Hello, everybody. Mr. Hinnon here, and here we are going to take some notes over Chapter 18. This is the beginning of a new unit. This unit is on electric forces, electric fields, and electric potential. So it's going to be a little bit of Chapter 18 and Chapter 19. It's also going to be a little bit of review. So we're going to zip through these pretty quick and see what we can kind of come up with. So let's see if I can get a pin here, and then we'll start. So first thing, obviously, we know that we've got atoms are going to have electrons, they're going to have protons, they're going to have neutrons. The mass of a proton and neutron are almost the same. So we often talk about that, where an electron is about 1,000 times smaller than that particular object. But that's not as much what we're concerned with here. We are concerned with charge. So I write this E equal 1.60 times 10 to the negative 19 coulombs, a good thing to kind of throw onto that equation sheet. But it describes the quantity of charge on an electron or a proton. They happen to have the same quantity of charge. They have a different sign. Obviously, we know electrons are negative, protons are positive, and then neutrons don't even have a quantity of charge. So in nature, when you have a normal atom here, so for example, if this was my atom over here, notice I have 1, 2, 3, 4 electrons, 1, 2, 3, 4 protons. That means it's electrically neutral. But if I were to remove some electrons or add some electrons, it would change that. And it's going to have a quantity of charge, a magnitude, that's going to be equal to the number of electrons I add or remove. So if I were to get rid of, say, this electron, all of a sudden now it has 4 protons and only 3 electrons, so it would have a quantity of charge of 1, because I've removed 1 electron, times that 1.6 times 10 to the negative 19 coulombs. So key idea to kind of keep in mind. The next thing, moving myself off of the piece of fur there, is we know that we can charge things up. When you rub your coat or you take off a sweater in the middle of winter, we know it tends to get that staticky feel. And really what that's called is triboelectricity. In other words, you're using friction between two objects to actually transfer charge from one object to the other. And we can look at a triboelectric series here. For example, this one, the top is going to be negative objects, and the bottom is going to be positive objects. So if I were to take, say, glass and rub it against silk, for example, what's going to happen is the glass is going to become positively charged, the silk would be negatively charged. Really what's happening is electrons are being transferred from the glass to the silk. The example they have over here, ebonite is really just a type of rubber material. And when you take that and rub it against the animal fur, then what you find is, since the rubber is up here and the fur is down there, the rubber is going to actually, or the ebonite is going to gain a negative charge, and the fur is going to lose those charges to that. And so we always talk about this triboelectric series and this transfer of charge. However, we have to follow the law of conservation of electric charge. This is the idea of good old Ben Franklin that we talked about last year. So Ben Franklin pointed out that you're not gaining or losing charge. He came up with the types of charges. And so you're going to gain as much negative as the object is losing. So it's going to become a quantity of charge that's negative, and the fur would have the same quantity of charge. It would just be positive. We also know this. This is another idea of good old Ben Franklin. We know that like charges tend to repel and unlike charges are going to attract. So they're showing an example here. And we have been talking about heat transfer. And so the cool thing is electricity can also transfer. We know it can stay on an object. So you can charge an object up by adding some electrons or removing electrons, excess electrons from it. But you can also get the movement of charge. And they follow the kind of the same pattern as heat. We've been talking about heat flowing from hot objects to cold objects. Well, electrons are going to flow from negatively charged object towards positively charged objects. And so we get this flow, and we talk about conductors and insulators just like we did with heat. One of the key ideas that we learned with Ben Franklin last year, that's really electrons that are moving. However, he didn't know that. He thought it was a positive fluid, and so we often talk about electric current or conventional current as a positive fluid, just like heat was, but now we know it's actually negative particles. So we'll talk about that later when we get into the electric potential idea. Zipping along. Oops. So there are different ways to charge things up. This is an idea that's known as like temporary induction. So when I bring a negatively charged ebonite object near some surface, you're going to get the opposite charge to kind of move towards it. So it would actually get a buildup of positive charge near the ebonite, which is negative, and the negatives would be on the opposite side of it. And so this is when you induce a charge, but this is just temporary, so a temporary induction. And then when you actually come into contact with it, then what you're going to do is, since it's got a positive near, since it has a positive near that setup, you're going to have some of the negative move onto the object, and the object will become negatively charged. This is charging by contact. It gives it the same charge. You can also charge by induction, which is when you bring the negatively charged object nearby, we know it's inducing this positive charge there. And then if I ground it or I connect it to something else, I give those negatives someplace to go. They can get farther away, and that's going to actually cause a permanent induction of the opposite charge. So the key idea with induction is it's going to always do the opposite of whatever you're using. So these were just some concepts that we had from last year. This is another concept from last year, Coulomb's law. So Charles Coulomb came up with a way of actually quantifying the amount of charge we have going on here. So we know that we have traction or repulsion between these charges. What we want to do is actually quantify how much attraction or repulsion we have. And so Coulomb's law came up with this idea. He really just kind of borrowed the idea of Newton's law of gravity, but did it with charges. So the electrostatic force between 2 point charges, Q1 and Q2, and we use Q because just like heat, quantity of heat, now it's a quantity of charge. So I often drop those absolute values because I think of Q as just being the quantity. It doesn't have a sign. They're putting those in there to remind you don't actually put the sign in. But it's also inversely proportional to the square of the distance. So in other words, as you get things farther and farther apart, that force is really going to drop off very quickly. And as you get them closer and closer together, they're going to really spike. Now, we learned it with this K value, the electrostatic constant, which was 8.99 times 10 to the 9th. Or sometimes I just round it off to 9 times 10 to the 9th, just to make it easy. It's just a constant that makes everything work in terms of units and the value. However, we can also write this electrostatic constant in terms of this little epsilon zero. This is called the permittivity of free space. It's a constant throughout the entire universe. And it has other functions when we get into electromagnetism and electromagnetic waves. So we'll bring that up later, but this is another quantity you'll see. And this is 8.85 times 10 to the negative 12. So K is actually equal to 1 over 4 pi times that permittivity of free space. For right now, I'm just going to continue to use K. I think it works fine. There is a place later that we're going to be using that epsilon zero, that permittivity of free space. We're going to take a look at some problems later, so I'm going to kind of skip over those. I'm just kind of going through some definitions. Most of these should have been review. This is now new. We didn't actually talk about electric fields last year because I just didn't feel like we needed to. But if I have some kind of test charge in here, and it's always scientists for some reason like to talk about positive test charges, then it's going to feel some kind of force. So this blue line here is representing the force, and it's caused by these other charges around. This is attracting it that way. This is trying to attract it that way. This is trying to repel it away. And basically when I combine all those together, we end up with this force. But a lot of times what we'll do is we'll take the force and divide by the quantity of this test charge, and we'll come up with a thing called the electric field. And we're going to play around with this again with an activity next week. But it's a great way to kind of look at not necessarily what the force on a particular charge is, but if I just have some charge sitting in space, how much force it has per unit charge. So the newtons per Coulomb. And it's basically the vector sum of all the forces. It's going to be caused by all the surrounding charges. So we have another nice little equation here that relates that. Now, if I have a point charge that's actually creating that electric field, sorry, my PowerPoint doesn't always like to stay in one place, but if I have some kind of point charge here, this is my point charge Q that's creating the electric field on some test charge over here. So this is my test. Then I create a force, but I also create an electric field. So I can take my electric field equation and I can take Coulomb's law and I can combine them together. I can smoosh them together and come up with one relationship. So basically, if the force is equal to this, I can substitute that in there. That's what I've done right here. And what you'll notice is Q2 ends up being my test charge. So it will cancel out with the test charge down here. And I end up with a neat little way of finding the electric field of a single test charge. And this electric field is only dependent on this charge. Notice that it does not depend on the test charge. We don't care what that test charge over there is, and that's why we often don't really even need it. So this is a great way of relating the electric field due to a single charge. So we'll play around with that as well. Electric field lines. I can't remember how much I did with this. We did do an activity. We're going to do this activity again this year with the electric field simulation. And it's a great way of kind of visually representing what's going on. So if I have some kind of charge here, a positive Q, for example, it's going to have electric fields that are basically pushing things away. And as scientists, we always define electric fields as the direction a positive charge would move in that region of space. And the more lines you draw means the stronger that charge is. So this is representing the electric field due to that little positive charge. They're always directed away from positive charges and toward negative charges. So this is a key idea here. Directed away and toward. So when you put a couple of charges together, this is a great little picture to kind of represent that the electric field is going to point away from this positive charge and then eventually kind of get sucked into this negative charge. And so we get these pictures of the electric field. When you get into college, if you take some more electromagnetism classes, EM classes, you might get a chance to actually map out electric fields. They're not the easiest thing to do. There's a variety of methods to do it. I usually just kind of represent them with pictures. I think that's good enough. And then this little statement at the bottom, the number of lines leaving that positive or entering the negative charge indicates something about how much the magnitude of that charge is. So different ways we can actually represent these electric fields. If we have two that are the same, this is always a key idea that I think is kind of neat. Notice that there is no electric field in the middle here. So the electric field in the center just kind of cancels. These electric field lines push against each other. One of the other key things you'll notice, these electric field lines never cross, because that doesn't make any sense. If I were to put a test charge right here, I want to know what's going to happen to that test charge. If I had electric field lines cross, it would have two methods, and I haven't combined them as vectors. Notice in this picture here, we didn't have any electric field lines cross. This picture didn't have any electric field lines cross, so we never have electric field lines cross. That brings me to a neat little concept question here. So there are three things wrong with this little picture here. So feel free to pause the video and kind of think about it. What do you think are wrong with this picture? Now, looking at it, there is one that I just mentioned. I have point P here as a point that the two lines have crossed over each other. So this can't happen. So you can't have them cross. That's number one. The other ones are a little bit harder. The next one most people kind of notice is we didn't have any pictures where the lines were straight. So this one doesn't seem quite correct. It seems like they should curve because they're going to go away from this charge, but then they're going to get pulled into that. So they tend to be more curves like we have down here. The third thing is a little bit harder to realize, but they put numbers on here. Notice they put 4, 1, -2, -1. And so what we're trying to represent is the number of field lines is going to be affected by that magnitude. We should have the most charge or most lines coming from this 4 in the center, and we should have more going to the 2 than are going to these 1s. It doesn't really matter how many we have, just as long as we have more. So if I was going to say this is 4 and I'm going to draw, let's say, 4 lines away from it, I might just have 1 line go over to here. I'd have 2 lines go over to here, and I would have just 1 line go to here. Or maybe I'm going to do 8 of them, and so I have twice as many there, but twice as many to that. When I put it all together, this is the picture that the book says is probably the best, and I think it's a really good one. Notice I don't have any of the lines cross. I have twice as many lines going to this -2 as is going to the -1s over here. They're more of a curved shape, and we get everything much better. The other key thing, this is kind of neat, and if you've ever dealt with buying electronic equipment, sometimes it'll come in an electrostatics shielding bag. And that's the reason why that is true is because when you have some kind of situation like that in equilibrium, there is never going to be an electric field inside of an actual charged object. It's always going to have an electric field that's equal to 0. And the reason why that happens is any charges that are on this object are going to tend to spread out as much as possible. So they're going to spread over the entire surface. And so you get all the charges on the surface and you get no charge in the center. And therefore, you actually have an electric field that's 0 at a point in the center of this. So putting some kind of, if you've ever heard of a thing called a Faraday's cage. So if you want to have some fun, look this up. It's basically a protective shell that'll make sure there's no electric field inside. There's a cool little movie called The Sorcerer's Apprentice, where he actually plays around with Tesla coils, and he has a wire cage around his controls, and none of the lightning bolts that he's creating go inside the cage because that's a Faraday's cage. It's basically like this. It creates that shielding. There's no electric field inside. The last thing I want to talk about is a thing called Gauss's Law. And Gauss's Law is something new that we haven't actually dealt with. A Gaussian surface is really just when you're dealing with any kind of vector quantity, usually it's going to be some kind of force like gravitational force or electric force or magnetic force. We can draw a Gaussian surface around it. It's just a theoretical kind of mathematical concept. Usually they're going to be spheres or maybe cubes or cylinders, something to kind of take into account the shape. So if I had this little point charge here, this positive charge in the center, and I drew a sphere around it, I know I have electric field lines going away from it. What we can do is we can actually determine a thing called the electric flux. And the electric flux is actually the product of the electric field times the area that it passes through. So this set of equations is just trying to showing how we can come up with that relationship. And one of the cool things is the electric flux is actually equal to the charge that's being enclosed divided by, hey, look at that permittivity of free space. So this would be the electric flux. And we often use the Greek letter phi to actually represent electric flux. Now, that works great if I have a nice little spherical where the electric field lines are passing straight through that surface. But I can also make Gaussian surfaces that are just kind of strange shapes. So this little blob around some kind of charge. And what you'll notice is that the electric field lines, they might be going kind of diagonally. They're kind of going all over the place. And so you might actually have the electric field going this way. What we want is we actually want, it's not just E times the area, it's actually the sum of all the electric fields times the cosine of phi, where we want to figure out what direction or the electric field that is perpendicular to that actual area. Later on, my calculus people, you're going to talk about things called dot products. This is actually a dot product that we're dealing with. So truly, the electric flux has a little cosine in there when we have the electric fields coming out diagonally to it. But we usually try to create Gaussian surfaces where that isn't a factor, where they're actually going to be perpendicular to each other, and then the cosine of 90 degrees is just 1, and so you don't have to even worry about that. So that's one of the ideas. Well, it's not, it wouldn't actually be the 90 degrees, it would actually be the cosine of 0 degrees, which is 1. Sorry, the angle here is actually the angle between the normal and the actual electric field. So this, when they're perpendicular to each other, so the electric field is pointed up like that, and your surface is that. So you have a flat surface with an electric field pointing upward. When they're perpendicular, the phi actually ends up being 0, so the cosine of 0 is 1. And so that's what we're dealing with. So this comes up with what is known as Gauss's law, which is just a way of finding it. And so we get this quantity here. This quantity over here is what we call the electric flux. We're also going to be talking about magnetic flux later. And we do actually need that permittivity of free space. So that's one of the reasons why we talk about it. It's just the charge, the entire charge that is enclosed divided by the permittivity of free space. That's the easiest way to actually find it. And you can calculate the electric flux. So that is a quick kind of rundown of everything in chapter 18 that we're going to need to know as we're getting into our study of electrostatics. Hope you enjoyed.